Are you ready? The third talk in this series of 3 talks to honor the birthday of Menachem. We have Menachem Magidor from Hebrew University Jerusalem, and the title is Singularizing Cardinals and Square-like Principles.
Does it work, the microphone? Yeah, okay, fine. Okay, it's a great pleasure to to be here in this program, but it's especially a great pleasure to be part of the celebration of Mirna's 50th birthday, which I find very, I must say, somewhat, should I say, shocked, in the sense that I always think about Mirna as being extremely young. And young not just because of the age or the way that she looks, but also because of the energy, because of the drive, the initiative. That's definitely something you go through with very young age. And discovering that she's catching up with us, the older people, I'm really concerned. But I'm sure that Mirna, being the wonderful mathematician, wonderful human being, will continue to have the same stamina, the same drive and energy that will definitely benefit both the scholarly work in mathematics, but also the kind of the social around it. Now, when I think about catching up, I couldn't resist showing a small video clip that probably some of you have seen before, which I like very much, which about catching up. By the way, I'm not very good at collecting pictures, so so I couldn't show many pictures like Jean have done with Mirna and memorizing, but definitely, okay. Why it doesn't work? Okay, that work.
Quiet. Stop here. Say you're 40 years old now. Wait a minute. Who's 40? Just say, pretend you're not 40. All right. Pretend you're not 40. All right, wait a minute. Look, pretend you're 40. Pretend you're 40 years old. And you're in love with a little girl, say, 10 years old. This one's going to be a pip. Well, now, wait a minute. I finish it. Now, I'm going around with a 10-year-old girl. Well, wait a minute. I got a good idea where I'm going to wind up. Will you wait a minute, please? Now, you're 40. She's 10. You're 4 times as old as that girl. Now, you couldn't marry her, could you? Not unless I come from the mountains. Now, never mind that. I'm asking you one little simple question. You want to answer it? You're 40. She's 10. You're 4 times as old as that girl. Can't marry her, so you wait. Oh, you wait 5 years. I wait 5 years. Now you're 45. The little girl is 15. Now you're only 3 times as old as that little girl, right? Huh? So you wait 15 years more. Now the little girl is 30, you're 60. Now you're only twice as old as that little girl. She's catching up. Yes. Now here's the question. How long do you have to wait before you and the little girl are the same age? Wait, now there's a very simple question. Hey, God. I mean, the whole thing is ridiculous. What's ridiculous? If I keep waiting for that girl, she'll pass me up. What do you mean? She'll wind up all in man. What are you talking about? She'll have to wait for me. Why should she wait for you? I was nice enough to wait for her. Oh, stop. She is anyway. She don't want to wait for me. I don't have to marry her. Marry her? She's a nice girl. Wait a minute. Quiet.
No, okay.
Look here. Say you're 40 years old.
I must tell you, the reason I was looking for it, I remember this particular clip of a part of a movie when I was 10 years old, and I remember how that was part of my mathematical discoveries. I mean, I realized I didn't have the exact term, but I realized that something like that doesn't matter how large constant you start. When this converges to 1 when n goes to infinity. So and I remember that I was really impressed by this fact following this movie. Okay, let's get down to business. And okay, it's this one and window view. Okay. Where is how do you do a full?
That's it.
Full screen mode.
Full screen mode. Okay, fine. Okay, so we are going to talk about singularized Cardinal square-like principles, an hierarchy of principles like that, and we see how, to what extent we can get models in which these principles fail. So we talk about squares and their friends, forcing failure of square-like principle singularizing and weak squares, and supercompact pseudo-prequy. I'm going to, some of the talks will be given on the board. There were a few things here were not quite correct on the slide, so I'll move to things in the board. So just to remind you, definitely for the hardcore set theorist, you don't need this reminder, it's so common, but for I think it's worthwhile to remind ourselves what is the Jensen square sequence. So we say that square holds at the cardinal kappa, square of kappa. If you can witness the fact in a coherent way, you can witness the fact that the ordinals less than kappa plus has cofinality at most kappa. Namely, for each alpha you find a closed unbounded subset of alpha. The order type is going to be at most kappa, and it's coherent. Namely, if beta is the limit point of C alpha, then C beta is nothing else than the initial segment in C alpha determined by beta. So if you think about it, of the picture, here is kappa plus. Here is a typical alpha. We know that the cofinality of alpha here is kappa. The cofinality of alpha is at most kappa, so there is a closed unbounded subset leading up to alpha. But which order type is at most kappa. But you want to do it in a coherent way, namely, that when you pick the sequence for alpha, you want that if something is a stage in the construction, a beta which is the limit point of C alpha, you want it that at C beta you already knew what is the choice that you made. Though you don't know alpha yet, you know the choice. And that's very useful in many constructions. Many combinatorial consequences, typically showing that reflection principles fail. You're able to define all kinds of counterexample to reflection principles by doing a construction inductively, where the square sequence allows you to bootstrap yourself up to the eventually getting to kappa plus. Many of these applications follow from the fact that square implies that every stationary subset of kappa plus is a stationary subset that doesn't reflect. So stationary square implies that stationary reflection fails very badly, and via that you can get a lot of failure of compactness properties, like for instance there exists a group of size kappa plus, which is every smaller cardinality subgroup is free, but the whole group is not free. There is a space such that every subspace of cardinality less than kappa plus is metric, but the whole space is not metric. There are all kinds of counterexamples to compactness follow actually from, some of them simply follows from this corollary of square, the non-reflecting of stationary set, and some of them you need a little bit more elaborate construction, but square is very useful for this kind of inductive construction. Now, it turned out to be useful and interesting to define weaker version of square. In square, when we add it, we reach a certain ordinal beta, then we have a C beta, we have a guess of a closed unbounded subset of beta, and we know that if beta is going to be used on the way to alpha, then C beta is the initial segment of what we are going to use. Now, the weaker squares is you simply try to get you allow yourself more than one choice at every stage beta. So now the square kappa lambda holds. Lambda is a parameter that tells you how many guesses you are allowing yourself at every stage beta. So square kappa lambda holds. If there is a sequence C alpha for alpha less than kappa plus, so that now C alpha is not one closed unbounded subset, but it's a family of closed unbounded subset of alpha. Such that for each member of C alpha, the order type of D is at most kappa, and you got the coherence. And the coherence now, since you're talking about more than one set, if D is a member of C alpha and beta is the limit point of D, then D intersect beta belongs to C beta. It appears already among the guesses in C beta. And the parameter lambda tells you that the number of guesses you got at every ordinal alpha is at most lambda. Now, of course, the usual square, you got only one guess, so it's equivalent to square kappa 1. The principal square kappa lambda are becoming weaker as a function of lambda. You allow yourself more and more guesses, then it's easier to satisfy. Now, one case is a special case where lambda is kappa. You allow yourself, remember, you are moving to kappa plus, you allow yourself lambda many, kappa many guesses. It's known also square star kappa, and it's equivalent to having a special ancient tree on kappa plus. And it automatically holds in case kappa to the weak power of kappa is equal kappa, which of course can hold only if kappa is regular. So if you have GCH, all the regular cardinals are automatically satisfy this weak square. Of course, there is a weaker version, which is square kappa, if you want to look at square kappa plus, but this is known as the silly square because it always holds. If you allow yourself kappa plus many guesses, then you can pick a guess which will lead you to any alpha less than kappa plus. By the way, surprisingly enough, even the silly square is useful sometimes, having a list like that. Okay.
Question?
Yeah.
What lambda is enough to give you a non-reflecting stationary set?
Lambda, anything lambda which is less than kappa give you a non-reflecting stationary set. If lambda equal kappa, then it is consistent that modular large cardinals, because then it is consistent that the principal holds and every stationary set reflects. That's a relatively old result of Cummings, Foreman, and myself. So, okay. Now, a property which is even weaker than the weakest square we mentioned, no, I'm not talking about the silly square, is approachability. So we said that approachability holds if there exists a sequence C alpha such that enumeration of candidates for approaching ordinals, such that for on a closed unbounded subset of kappa plus, for technical reason of simply enumeration, you need to do it only for club many alphas. You can find, you can be in such a way that for club many alpha, C alpha is a closed unbounded subset of alpha. Its order type is correct. Now, as far as the guesses, if beta is the limit point of C alpha, then C alpha intersect beta is not necessarily C beta, but it appeared somewhere in the list before alpha. Then you approach alpha, you approach alpha by a closed unbounded set whose order type is at most kappa, in such a way that every initial segment really appeared in that enumeration before alpha. And that's also useful for combinatorial for several combinatorial construction. For instance, it implies the now I'm becoming more technical concerned with the PCF. It implies the existence of good scale and some other properties.
Do you mean C gamma intersect beta?
Sorry?
C alpha intersect beta equals C gamma intersect.
For some gamma less than alpha.
Yeah, but
It's actually equal, or it's equal when you intersect it with beta?
Intersect beta. Namely, if you have a beta which is the limit point of C alpha,
Yeah.
then you look at C alpha intersect beta. That's the initial segment. You say that appeared.
supremum must be beta.
Sorry?
C alpha intersect beta, supremum is beta, isn't it?
The supremum is beta, but it's equal to C gamma for some gamma.
Yeah. We'll look at property 1. C gamma is club and gamma.
C gamma is club in gamma.
Not necessarily. I didn't say so. I didn't say that gamma could be even a successor. Remember, the C alpha is a closed unbounded subset only for club many alphas.
Okay.
I'm allowing myself space. The reason it's club many alphas, I'm allowing myself space to enumerating initial segments of things.
I withdraw.
Thank you for clearing that up.
So this is exactly the reason I'm allowing myself that C alpha is a closed bounded subset of alpha only at club many alphas. Well, only it's most alphas in a way, but that you have you have space to enumerate initial segments of C alpha for the majority of the alphas. Okay, so now all these square-like principles are rather robust. They are robust in the sense that suppose that you start with a universe of set theory V, and you extend it to a universe W by forcing or other way, and kappa is the cardinal of W, or the bigger one, such that both models compute the successor correctly. Then if V satisfies one of these weak squares, then the same sequence is a witness to the square in the bigger model. What does that mean? That means that in order to kill, in order not to avoid having a square, you must collapse cardinals. There is no way you can preserve cardinals. You can preserve kappa and kappa plus and lose the square sequence. And a similar result also, of course, for approachability. So there is a certain robustness for these properties that once you have them, then it takes some effort to get rid of them. This is especially significant, of course, when you talk about singular cardinals, because if kappa, think about a case where kappa is singular, then you have to collapse its successor, and that's usually something that. So we got an hierarchy of.
In the previous thing, can you sort of can you recover the previous? So W has some sort of square sequence. Can you recover the square sequence that is there on V from it? Or
No. You can be in a situation where V doesn't. It goes upwards. It doesn't go downwards. Namely, you could start with the situation that there is no square in V in the smaller model. You can force square without collapsing cardinals when you move to the bigger model. So you have the square or the weak square or whatever you want in the bigger model without having in the smaller. It goes upwards, not.
What I meant was that V has some square sequence and W does as well, but is there some relation between the two square sequences?
Well, there is a trivial relation that the square sequence of V is also S square sequence for W. A square sequence is not necessarily unique. So if you got one which is example for V, it is an example.
The same one suffices.
The same one suffices. But you could have something which doesn't come. You could have a new ones. You can change it. But the fact that you have a square sequence is. By the way, I appreciate this. You shouldn't. It's a challenge to give the last talk of the day after a long day, and the fact that at least some of the audience is awake. I think it's something to be cherished. Okay, so we got this hierarchy of square-like principles, and by the way, they are it's strictly increasing, decreasing in strength. Namely, it becomes weaker and weaker, strictly weaker. Now, where do we have these principles? In all the canonical inner models for moderate large cardinals, the square holds everywhere. We have it, the thing is true for every kappa. In L, if you talk about L of mu, L of, for a measurable cardinal, the canonical inner model for Woodin cardinal, for quite a while, in the inner model it's true for all kappa. Even when you get, we'll get in a short while to cardinals which actually block square, then still in the canonical inner model, to the extent that they exist, some of them do not exist yet, then the square fails only on a very particular point. Now, on the other end, above very large cardinals, square in square principles fail, and there is again an hierarchy of how much in this hierarchy, if you think about the you know, it's a weaker thing. So the point is, where does it, which of these principles, what is the strongest principle which is still holds in the presence of this large cardinal is something which is an interesting measure of the largeness of the cardinal. So, for instance, very large cardinal imply the failure of square-like principles. So, for instance, the result of Solovay that says if kappa is strongly compact, then square lambda, the old square with one choice, fails for above the strongly compact. It fails everywhere. By the way, below the strongly compact, you can have unboundedly many places where it holds, but that's another story. Now, if kappa is super compact, then square lambda lambda fails for every singular lambda whose cofinality is less than kappa. So if you talk about kappa, which is super compact, here's kappa super compact, and now you got lambda that the cofinality is less than kappa. This is cof lambda. Then square lambda lambda, the weak square fails, and actually even stronger than that, the approachability fails. This is a slight modification of the argument of Shelach. Now, for others, that the cofinality is different, then it's actually a result of several other people, but Berk and Kanamori summarized it by saying that square kappa lambda mu fails for lambda above kappa for mu less than the cofinality of mu is less than cofinality of lambda. Square lambda lambda can hold if lambda is not of this form. By the way, these results are tight, are accurate. You can force, starting with supercompact, you can force anything that doesn't fall under these cases to have exactly the kind of square principles that is allowed by this statement. Now, the first place in the hierarchy of square-like principles that can hold is intuitively measure of how you close to inner model and to what extent you are to the kind of canonical L-like models, and to what extent you are closer to something that smells like a little bit like supercompactness. So it's interesting to classify to what extent where the square principle fail. Let's pick an example. We got two forcing axioms: PFA, the forcing axiom for proper forcings, and MM, the Martin maximum. Now, Tudorcevic has shown the PFA shows that square lambda fails for every uncountable lambda. Namely, everywhere. It's a little bit like Solvay results for strongly compact. It fails everywhere. Now, you can easily strengthen the Tudorcevic argument to show that square lambda omega 1 fails for every uncountable lambda. Namely, you cannot allow yourself omega 1 many guesses and have the square sequence. On the other end, omega 2, it is consistent that that square lambda omega 2 holds for every lambda. That you can have omega 2 many guesses. What's the difference between omega 1 and omega 2 in this case? It's simply that under PFA, the continuum is omega 2. So you can have anything, in some sense, something which is less than the continuum. Well, you don't have too many possibilities. PFA implies the continuum is exactly Aleph 2. So you can have, but you can't. But square lambda omega 2 is consistent with PFA. On the other end, if you consider MM, then the situation becomes more restrictive. So, for instance, if the cofinality of lambda is omega, then the approximation property fails. That thing about the example of the supercompactness, that this is a thing about if kappa being cofinality being omega is being, having small cofinality being above omega 1, then the approximation property fails. The weakest property in its hierarchy going to fail. If the conformality is exactly omega 1, then square lambda mu fails for every mu less than lambda. Now, if the conformality is bigger than omega 1, then square lambda mu fails for every mu less than the conformality of lambda. Now, again, this is tight. In the same paper with Cummings, we show that you can force a situation which exactly lambda which do not satisfy these properties exactly. You could force the strongest square which is compatible with this with these restrictions. Okay, so now how do you get failure of in general the consistency of failure squares? So getting it at or what's the consistency strength of failure of square? I mean, we've seen that some very large cardinal apply the failure of square. So I think that I wasn't able when I prepared it to check. I must confess I've done the preparation yesterday, last night, and the internet doesn't work in the apartment for some reason. I think it's due to Jensen. That if you want to get square to fail at a regular cardinal, then that's relatively easy to arrange. You don't require, the consistent strength is not too large. You take a lambda which is a malo cardinal. For us, malo cardinals are tiny. And you Levi collapse all the cardinals between kappa and lambda to kappa. Then square kappa mu fails for every mu less than kappa. So the first square that could potentially hold would be square kappa kappa, and in fact it does hold square kappa kappa in this model because kappa is regular and kappa to the big power kappa is, when you collapse malo, is kappa. So in that case you do get square kappa kappa. If you want square kappa kappa to fail at a regular, then you need a more complicated technique which is due to Bill Mitchell, that you must somehow mess up generalized continuum hypothesis. So there is a construction in which you start with a malo cardinal, and you can find a forcing extension in which lambda is successor of kappa and square kappa kappa fails. Now, what about the weaker thing about approachability? Here we have a freedom. You could have in the model, if you do it one way, approachability will be true. If you do another way, approachability will be false. You can have your choice. So getting failure of square at regulars is relatively, the consistency strength is not too large. Now, what is the consistency strength of the failure of square, or the weaker version of square, at a singular cardinal? So this is a question which is really still open. We don't know what consistency strength of that thing is. And let me tell you what's on. It definitely requires much larger cardinals, because see the following situation. Remember the thing about the robustness of the property. And now suppose you start from L. Here is L. Here is a singular. Here is kappa plus. Suppose that kappa is singular in V. Suppose that conformality of kappa is less than kappa in V. Now, if zero sharp does not exist, if relatively large or moderate large cardinals do not exist, then you got covering theorem by Jensen, covering theorem. That means that kappa is singular. That implies conformality in L of kappa is less than kappa, and also that you compute the successor of kappa correctly. The successor in L is the same as the real successor. But in L, in the constructible universe, we already mentioned you do have square. Therefore, you are exactly in a situation where a square in L implies square in V. So that means that if, let's say, zero sharp do not exist, then necessarily you must, then at singulars, cardinals, you necessarily have square. And the same argument works for inner models for larger cardinals. As long as you got some kind of covering, as long as you have, you can show that you have square in that model. So if you try to find the exact place where we don't have square, or it implies, so here is something which is probably the consistency strength of the failure of square at singular. So we said that the cardinal is said to be subcompact. If for every structure of the form you look at H kappa plus, H kappa plus is the set of sets of hereditarily of cardinality less than kappa plus. So you look at H kappa plus, epsilon, and you got some predicate. And you say that it's subcompact if for every structure of this form you can find elementary substructure. You can find some, suppose this structure is A. You can find a B which is elementary substructure, such that B, when you, B of course is isomorphic to a transitive structure. When B is isomorphic to something of the form H mu plus epsilon B. Namely that you got something that looks like, for a smaller mu, looks like the structure H of a mu plus with some, together with some predicate. Now it's relatively easy to show that if kappa is subcompact, then square kappa fails. So this is the first or the minimal notion of large cardinals we know about, that simply the large cardinal itself implies that at the large cardinal square kappa fails. This is some kind of reflection property that is inconsistent with square. Now we have some evidence for that's the case. That because there is a result, I didn't put it on the slides. There is a result of Schimmerling and Zeman that shows that suppose you construct a kind of canonical inner model for that may contain subcompact cardinal. Then, or a model that doesn't contain a subcompact cardinal, model of the form LE. Then square also everywhere. So it seems like it is the natural thing. The issues are to get such inner models, but that's another thing. Now, suppose so this talks about failure at regular, which the consistent strength is not very large, but with the relatively slight modification, we can make it into a statement about failure of square at singular. And that's a very simple argument of Martin Zeman that tells you that suppose you got a subcompact cardinal which is also measurable, itself is measurable. By the way, this definition does not imply measurability. It implies some measurables below, but it doesn't imply measurability of the cardinal. Okay, so if it is consistent to have a subcompact cardinal which is measurable, then it is consistent that square kappa fails for some singular cardinal. What is the argument of Zeman? It's rather simple. You start from a kappa which is measurable subcompact, therefore it is no square, and you use pre-forcing for changing its cofinality to omega. And you use the fact that if kappa is measurable cardinal such that at kappa, we happen to have that kappa, square kappa fails, then if one forces with pre-forcing for kappa, then in the resulting model, the square still fails. You are able to show that if the pre-forcing introduces a square sequence for kappa, then the square sequence, a square sequence must have existed in the ground model. But by pre-forcing you can't do it. Well, what about weaker squares? I mean, suppose you start with a cardinal that weaker square, I don't know, even supercompact or something like that, and you want to singularize it and get failure of square that cardinal. Well, if you try to pre-cree, now there is a surprise, because the theorem of Cummings and Schimmerling tells you that if kappa is a measurable cardinal, if you force with pre-forcing, then in the resulting model, well, square kappa, maybe it's not true if it wasn't true in the ground model, but square kappa omega is true. You can have, if you allow yourself omega many guesses, then you do have it automatically. It doesn't matter what the ground model, if it was measurable, you change the cofinality of kappa to omega, you force with pre-forcing, automatically square kappa omega is going to be true. And we are talking about pre-forcing. In a minute, we'll see that this is much more general, and here we are connected to the work Mirna and Saron, and in a minute we'll talk about that. Okay, so what are the properties of the pre-forcing? So the property of pre-forcing, you start with the measurable cardinal model of theory. I don't know what's impossible. It's of course inaccessible. Okay, so now suppose we force with the pre-forcing. Now we didn't collapse the successor. Pre-forcing doesn't collapse the successor, and we have an omega sequence which is cofinal in kappa. Now the pre sequence cofinal in kappa has the following properties. For large enough n, alpha n is regular. From a certain point on, the canonical pre sequence, if you use a normal ultrafilter, is going to be a regular cardinals. I'm more interested in the fact that I want to be just the fact that they are uncountable cofinality, uncountable V cofinality. Of course, we get more, but and now if you use a normal ultrafilter to do the pre-forcing, then every closed and bounded subset of kappa in the ground model, eventually this omega sequence is going to be there. This omega sequence gets through all the clubs, all the closed and bounded subset that belongs to V. So now let us make a definition. You got two models of transitive models of set theory. A kappa is the regular cardinal in V. A sequence is said to be kappa pseudo pre sequence over V if for every club, eventually club that belongs to V, closed and bounded subset in V, the sequence is eventually in the club, and the cofinality is uncountable. We're going to make requirements of. Okay, so now a result of paper of Mirna and Shelach, and independently was done by Gittig. The paper of Mirna and Saron contains many other results. It tells you the following thing: that suppose that V are two transitive models of set theory, and in such a way that you got an inaccessible kappa, and so suppose it satisfies GCH. You can, in the paper, it's a little bit. You can weaken it a little bit, but in W kappa it's got. And now when you extend, when you move from V to W, here is V, here is kappa. Kappa is inaccessible here. You move to W. Now in W, here it's kappa is regular. Kappa becomes singular, and the cofinality of kappa. I mean, the result talks about cofinality, but I'll be limited our attention to the cofinality omega. And suppose you didn't collapse kappa plus, then automatically there must be a pseudo pre sequence in W. You must have introduced a pseudo pre sequence for W. You must introduce a sequence that eventually meets every. Eventually is in every closed and bounded subset of kappa. Now, actually, I don't think I've tried to look in the paper. Mirna, maybe you remember that it's an old time ago when you were even much younger. There is essentially implicit an argument that shows that in this situation. Square kappa omega holds in W, but you never stated. It's never stated, and I suspect that it's partially because you were interested in not just cofinality omega, but the general case in which it is not known whether it's not known. So I think that's.
Yes, and we were all very interested in this functional square.
Yeah. Anyway, so implicit in the Lamonja Shelach thing is the fact that in that situation you have square kappa omega necessarily hold. Let me very briefly show. And now I want to move to the board. Maybe partially I have to embarrass. There were certain statements in the slides that I prepared, which are not quite correct, so I think I'll. Maybe we can even turn. Can we simply even turn off the?
The projector?
Yeah.
Oh.
Something happening? Oh. Okay.
You just need to look at the
Okay, so now comes the following lemma or theorem or whatever you want to show it. It says the following thing, that suppose that we got V is subset of W, and exactly the same situation, and suppose that, what's a,
just Yoko just moves and things happen, you know. And you know, something.
well, Yoko is a very powerful, and suppose that in V we are default situation, kappa is regular. In W, cofinality of kappa is omega, but kappa plus in the sense of V equal to kappa plus in the sense of W. And there is a pseudo precree in W. There is pseudo precree over V. Then I claim that square, then in W square kappa omega holds. What you said, I'm sure, as I said, it's implicit, but probably in print it will be the first time in the paper with Dima that many results that are writing. Okay, now let me roughly give you the idea of the proof. We use the fact that in V, kappa is regular, and therefore fix chi large enough, you know, such that h chi contains all the relevant large enough, and let for every alpha, for alpha less than kappa plus, fix a continuous increasing sequence of elementary submodels of h chi, such that alpha itself belongs even to the first one. Oh, but by the way, h chi, I assume that it endowed with some fixed well ordering. Alpha 0 belongs to alpha belongs to M0. The cardinality of M alpha, the sequence M rho, cardinality of M rho is less than kappa. And the union, of course, will cover all of the union of M rho covers kappa. By the way, which means it will cover all of alpha, because alpha has got cardinality kappa by elementarity. Cardinality kappa, M rho intersect kappa is the ordinal. Okay, that's it. So now we know that the set, the following set is a club. The set of alpha such that M rho intersect kappa is exactly rho. The set of rho is a club in kappa. This is all done in V. Kappa is regular, so you can do all this construction. Now we know we can use the pseudo precree. We can use the pseudo precree. So let rho sub n be the pseudo precree. Let rho sub n for n let omega be in W pseudo precree over V. So now I'm going to tell you what is the, remember, I want to show square kappa omega. So I have to for each alpha, I have to find out a family. I have to find out the family of countably many subsets of clubs in alpha that will be used as a square. So what I'm doing, I'll take those m's so that their index belongs to the pseudo-precursor sequence, provided, of course, that m is cofinal in alpha, but maybe m is not a closed set. Then I simply take the closure of it. So I'm considering the set of so C alpha, the family C alpha, is made up of m rho provided of rho n provided rho n belongs to E alpha, belongs to this club m rho n, and now I take provided m rho n is cofinal in alpha. Maybe it's not, it's definitely going to be cofinal, but what about closure? So I take the closure of that. Simply, I mean the closure of the, it's a set of ordinals, so the ordinals there I simply take the limit ordinals. So now what do we know about C alpha? Well, why it's not non-empty? Well, definitely non-empty for alpha. If the cofinality of alpha in V is less than kappa, then C alpha is not empty. Because one of the M alphas, cofinality is less than kappa. The union of all these M rows is going to cover all of kappa. In particular, it goes at some point past the cofinality of alpha. Once it passes the cofinality of alpha, it will contain a cofinal sequence in alpha. So that's now another thing, which takes a little bit of argument. I will not do it. M rho n is omega closed, or intersect kappa is omega closed in V. Here we use the fact that the cofinality of rho n is uncountable. You can show that M rho n is omega closed. Okay, so now, so C alpha is a collection. Forget for a minute about those alpha that got cofinality. Forget about alpha that got cofinality. Those alpha that got cofinality kappa. So C alphas, what do we know about C alpha? Its cardinality is at most aleph 0, right? You got only aleph 0 many things. It's made up of clubs in alpha. The order type is less than kappa because the cardinality of each M alpha is less than kappa. So it's a good candidate for being a square sequence. What's the only thing we have to check is the coherence. We have to check that if D belongs to C alpha and beta is a limit point of D, then D intersect beta belongs to C beta. That's what we have to check. Okay, so now let's look at beta. Note one thing. Why does D belong to C alpha? That means because D is the M rho n intersect alpha for some n. Okay. So now beta is the limit point, the closure of that. Beta is in the closure of that. So now let's see. If the cofinality of beta is omega, that implies that M rho n intersect alpha. If the cofinality of beta is omega, it's a limit point of D. Therefore, it's a limit point of M rho n. M rho n is omega closed. Therefore, beta belongs to this one. But if beta belongs to this one, by elementarity, really beta is less than alpha. So it really determined the intersection of this model with M really determined by the if beta is there, it knows about the function that maps beta to kappa. So the intersection with kappa really determines the intersection with beta. So that means that m rho n of I should have put an index for the m's. I defined it initially separately for each one of them, but that means beta is there. That means that m beta n alpha intersect beta is the same as m beta rho n intersect beta, because they have the same intersection with kappa. The intersection with kappa is rho n. This one knows about beta, therefore it knows about the minimal function mapping beta to kappa. This one knows about the minimal function, therefore the intersection is the same. They've got the same intersection. But this means that the closure, the closure of this belongs, if you take the closure of this belongs to C beta by definition. And this is exactly D intersect beta. So that's the case that beta has got cofinality omega. Now, if beta has got cofinality cofinality bigger than omega, then look at what beta is belongs to the closure of m rho n intersect alpha. So it's a limit point of m rho n. Well, if it is in m rho n, then it's the same argument. If it's not, it's in the closure. But so there exists unbounded set. But since m rho n is omega closed, there exists an omega closed set, right? The same thing would be true for the m rho n of beta. Now the intersection of two omega closed set of the thing is also unbounded in beta. So that means that m rho n alpha and m rho n beta has got unbounded intersection with, their intersection with beta is unbounded. The same argument now shows that their intersection with beta must be the same. Must be the same. So it satisfies coherence, and therefore it is satisfies coherence, and therefore it is it does form a square sequence. Well, I was cheating a little bit because I didn't take care. I was talking about alpha, which cofinality is less than kappa. What about if the cofinality of alpha is kappa in V? What is its cofinality in W, in the extension? Kappa changes cofinality to omega. So alpha has got cofinality omega. Cofinality, dealing with ordinals, if you've got a problematic set, of ordinals of cofinality omega, I can easily take care of the square. Simply, for each one, take an omega sequence leading to it. That doesn't conflict with anything on the square. These sequences have no limit points. I mean, the square requirement about square is that it's a limit point. So I can always extend the sequence to have. I can always extend the sequence to have to be a square sequence, and we are fine. Now, one thing about the proof. In order to get, we needed this pseudo-prequist sequence. In the Shelach-Gemonja, they required the 2 to the kappa must be equal to kappa plus. But note that in the proof, we didn't have to use the full strength of the thing being an omega, a pseudo-prequist sequence. There were only, there were actually a list of kappa plus many clubs which we want to be eventually in them. These are the clubs, the E alphas. There are only kappa plus many clubs which we want to meet. So it's enough to have pseudo prequel which meets only this alpha 1 many clubs, this kappa plus many clubs. But for that you don't need cardinal arithmetic. The Gemonja Shelach argument works for if you got a list, particular list of kappa plus many, you can localize it. Kappa plus many clubs, you can find the okay. So what does that mean? That means that if we anyway we change the cofinality of kappa to omega and preserve kappa plus, we are stuck with square kappa omega. We didn't. Square kappa omega is there. And there to stay, provided we destroy cardinals. Okay, so but a crucial thing in this argument was the fact that kappa plus was not collapsed. Now there is kappa plus was not collapsed. But could you singularize kappa while collapsing, let's say, kappa plus, collapsing more? There is a way. There exists a version, a supercompact version of pre-Cree. There is a supercompact version of pre-Cree sequence. Namely, you shoot of supercompact version of pre-Cree. Namely, you start with you force actually a sequence Q, and you look at P kappa of, let's say, kappa plus, or let's say general cardinal lambda, or let's say kappa plus. You shoot a Qn, n less than omega. Members of Qn of the P kappa of kappa plus is the set of subset of kappa plus of cardinality less than kappa. They are increasing, and they cover the union of Qn covers all of kappa plus, which means in particular that kappa becomes cofinality omega, kappa plus becomes cofinality omega. If you do it for something bigger, then it is. So now you could you can ask yourself: is there a version of the Jamonja, of the Mirna and Saron, thing existence of pseudo pre-Cree for this supercompact version? And the answer is yes. This is a result, joint result with Dimas in Apova, which tells you that well, at least if you do it for finitely many gap of finitely many steps from kappa, namely, let me state the theorem. This is myself plus Apova. It says the following thing. Suppose that you got again V subset of W, and suppose that the cofinality kappa is, let's say, regular in V, and suppose that W in W you have the following situation: that the cofinality for every k less than m, cofinality of kappa plus k is omega. Namely, you changed the interval. Here's kappa plus m. All these cardinals in between, the finitely many cardinals, were changed to cofinality omega. Then there is a supercompact pseudo pre-Cree for square for P kappa kappa plus m. What does it mean, a pseudo pre-Cree? It means an increasing sequence in P kappa, Qn. What is equivalent to the thing about that meeting? There is a notion of closed unbounded subset of P kappa of lambda in general, that for every club, or if you got list of kappa plus m plus 1 clubs, you can meet, you eventually are in the sequence. Corollary, if you are trying to avoid having weak squares by singularizing and collapsing, not just collapsing kappa plus, kappa double plus, at least for finitely many, you're not getting away from the weak square. So the theorem would be, suppose that again V is subset of W, I'll finish with that. V subset of W, V thinks that kappa is regular, and in V, just again, then in V, I'm sorry, in W, for all k less than m, cofinality of kappa plus k, kappa plus k is omega, but kappa plus m is still a cardinal. Namely, kappa plus m still a cardinal. Namely, in particular, kappa plus m of v is really the kappa plus in the sense of w, right? It's a successor of kappa. Then square, then you got square kappa omega is true in w. You didn't get away from square kappa omega. Okay, so it means that getting rid of weak square, of the weaker version of square, seems to be a difficult thing. And that's, I think that it's some indication that maybe the consistency strength, that we know we got an upper bound, the Zeeman result, but consistency strength of failure of square at singular, maybe the consistency strength of failure of weaker version, even square kappa omega, it's super compact or something of that order of magnitude. Maybe that's what this indicates. But we don't know. We don't have a lower bound. Okay, thank you.
Are there questions or additions or please?
What about this square version with parentheses? It seems that it is not preserved even if kappa plus is preserved in the extension.
Yeah. That's it doesn't have the same robustness.
Yeah. So I don't know if there are like similar results involving this principle, or for weaker versions.
Well, definitely, you know, the square, this kind of square, definitely gives you, square of kappa plus. It gives you a sequence that cannot be threaded, right? So it cannot be threaded in an absolute sense. So the issue is, so since we find it difficult to find models where square, even this square fails for square of successive singular, probably it will be difficult in that case. I don't know whether I'll answer the question.
I don't know if I mean, this is kind of parentheses square are relevant to solve also this kind
It could be relevant. It could be definitely relevant.
Okay, over there.
So I had some really short questions about silly square, one silly and one less silly. So the silly one, if you weaken ZFC, does silly square have any strength, assuming you've got a nice theory of ordinals as well to go with it?
When you say weaken ZF, I mean, what do you mean?
Yeah, so
drop choice, for instance, or
drop choice, drop power set, put in a collection scheme, something like that, work in those models.
It does have strength. I mean, of course, it's supposed to drop choice. Now, the fact that you can find, for every ordinal some way of witnessing its singularity, that by itself is already some kind of choice.
Yeah.
So it's.
There is a determinacy principle, also called the weak square, by the way, that says precisely that in the determinacy world. There is an AD version of weak square that says exactly.
Sure. Yeah. By the way, the failure of weak square, failure of square or even weak squares at singular, that implies AD LFR, of course, because it implies inner models. For every real, you got inner model for, with enough Woodin cardinals, and because the inner model for Woodin cardinals square all, so you've got failure of.
Other questions or comments? So let's thank Menachem.